Imagine a journey to the edge of reality, a place where gravity reigns supreme and the fabric of space-time is stretched to its breaking point. This is the realm of black holes, celestial objects so dense that nothing, not even light, can escape their grasp. As you approach a black hole, its immense gravitational pull would begin to distort your perception of time and space. The universe around you would twist and warp, stars would smear into streaks of light, and your own body would be stretched and squeezed in a process known as spaghettification. The closer you get to the black hole's singularity, the point of infinite density at its core, the more extreme the effects of gravity become. Time itself would slow to a crawl, eventually coming to a complete standstill at the event horizon, the boundary beyond which escape from the black hole's clutches is impossible. Falling into a black hole is a one-way trip to oblivion, a journey from which there is no return. The holographic principle, a mind-bending concept born from the study of black holes, proposes that the universe is like a hologram. Just as a two-dimensional image can encode all the information needed to create a three-dimensional illusion, the holographic principle suggests that our three-dimensional reality might be an emergent property of a more fundamental two-dimensional reality. This idea, as counterintuitive as it may seem, arises from the observation that the information content of a black hole is proportional to its surface area, not its volume, as one might expect. Think of a trampoline. If you place a bowling ball on it, the trampoline will stretch and deform, creating a dip in the surface. The deeper the dip, the heavier the bowling ball. Similarly, black holes create a dip in the fabric of space-time, a gravitational well that warps the surrounding space and time. Now, imagine placing a soccer ball on the trampoline. The soccer ball will also create a dip, but a much shallower one than the bowling ball. Even though the soccer ball has a larger volume than the bowling ball, it carries less information about the trampoline's curvature. The holographic principle extends this analogy to black holes. The information about the black hole's interior, including all the matter it has swallowed, is encoded on its two-dimensional surface, the event horizon. This suggests that the universe itself might be like a giant hologram, with all its information encoded on a distant two-dimensional surface. To grasp the essence of holographic duality, we need to delve deeper into the nature of gravity and its relationship to space-time. Einstein's theory of general relativity revolutionized our understanding of gravity, describing it not as a force, but as a curvature of space-time caused by the presence of mass and energy. Imagine space-time as a vast, stretched trampoline. If you place a bowling ball on the trampoline, it will create a dip, representing the curvature of space-time caused by the bowling ball's mass. Now, imagine placing a smaller ball, like a soccer ball, on the trampoline. It will also create a dip, but a much shallower one. This demonstrates that the degree of curvature, and hence the strength of gravity, depends on the mass of the object. Black holes, with their immense mass concentrated in a tiny region, create the most extreme curvatures in space-time, forming deep gravitational wells from which nothing can escape. The holographic principle suggests that the information about the black hole's interior, including all the matter it has swallowed, is encoded on its two-dimensional surface, the event horizon. This is akin to saying that all the information about the objects on the trampoline, their mass, position, and movement, can be encoded on the trampoline's two-dimensional surface itself, without needing to know anything about the objects themselves. The event horizon of a black hole is a boundary of no return. Once an object crosses this threshold, it is inevitably pulled towards the singularity at the black hole's core. The event horizon is not a physical barrier, but rather a region of space-time, where the gravitational pull is so strong that even light, the fastest thing in the universe, cannot escape. Imagine a waterfall. As water flows towards the edge, it accelerates, reaching a point where the current is so strong that nothing can swim upstream. This point of no return is analogous to the event horizon of a black hole. Anything crossing the event horizon, whether it be matter or light, is inexorably drawn towards the singularity, where it is crushed out of existence. The event horizon is also the key to understanding the holographic principle. The information about a black hole's interior, including all the matter it has consumed, is encoded on its two-dimensional surface, the event horizon. This is like saying that all the information about the water flowing over the waterfall is encoded on the two-dimensional surface of the waterfall's edge, without needing to know anything about the water itself. Section 5. Soccer balls and information, the paradox of black holes. The concept of information plays a crucial role in our understanding of black holes and the holographic principle. In physics, information refers to the specific properties of a system, such as the position and momentum of particles. The laws of physics dictate that information cannot be destroyed, only transformed. This principle, known as the conservation of information, poses a paradox when applied to black holes. Imagine throwing a soccer ball into a black hole. The soccer ball carries information, such as its mass, color, and trajectory. As the soccer ball crosses the event horizon and disappears from view, it seems like its information is lost forever. However, the conservation of information tells us that this information cannot simply vanish. This paradox led to a debate among physicists about the fate of information falling into black holes. Some argued that information is indeed destroyed, violating the fundamental principles of physics. Others believed that information must be preserved somehow, even if we don't fully understand how. The holographic principle offers a potential solution to this paradox, suggesting that information is not lost, but rather encoded on the black hole's event horizon. Holographic duality is a remarkable concept that connects two seemingly disparate theories: quantum mechanics, which governs the behavior of particles at the atomic and subatomic level, and general relativity, which describes the large-scale structure of the universe and the force of gravity. Holographic duality suggests that these two theories, despite their apparent differences, are actually two sides of the same coin, describing the same underlying reality in different ways. Think of two different maps of the same city. One map might show the streets and buildings in detail, while the other might focus on the city's transportation network, highlighting subway lines and bus routes. Both maps represent the same city, but they provide different perspectives and emphasize different aspects. Similarly, quantum mechanics and general relativity provide different perspectives on the universe, but holographic duality suggests that they are ultimately describing the same underlying reality. This duality is particularly relevant in the context of black holes, where both quantum mechanics and general relativity play crucial roles. Holographic duality suggests that the information about a black hole's interior, described by quantum mechanics, can be encoded on its event horizon, described by general relativity. This connection between two different descriptions of the same system is a testament to the deep interconnectedness of the universe. In recent years, physicist Enrico Rinaldi and his team made significant strides in understanding holographic duality and its implications for black holes. Using sophisticated computer simulations, they explored the behavior of a type of black hole known as a quantum extremal surface, a theoretical construct that sheds light on the interplay between quantum mechanics and gravity. Rinaldi's work focused on calculating the entanglement entropy of a quantum extremal surface, a measure of the quantum entanglement between the black hole's interior and its exterior. Quantum entanglement is a bizarre phenomenon, where two particles become interconnected, even if they are separated by vast distances. Measuring the entanglement entropy of a quantum extremal surface provides insights into the information content of the black hole and how it relates to the holographic principle. Rinaldi's simulations demonstrated that the entanglement entropy of a quantum extremal surface is proportional to its area, not its volume, consistent with the predictions of the holographic principle. This finding provides further evidence that information is indeed encoded on the black hole's event horizon, supporting the notion that the universe is like a giant hologram. The implications of holographic duality extend far beyond the realm of black holes, potentially revolutionizing our understanding of the universe as a whole. If the holographic principle is correct, it suggests that our three-dimensional reality is an emergent property of a more fundamental, two-dimensional reality. This is a profound shift in perspective, challenging our intuitive notions of space and time. Think of a movie projected onto a screen. The movie itself is a two-dimensional image, but it creates the illusion of a three-dimensional world. Similarly, holographic duality suggests that our three-dimensional universe might be a projection of a more fundamental, two-dimensional reality. This two-dimensional reality might not be located in a specific place like a screen, but rather exist as a mathematical construct that encodes all the information of our universe. This concept has profound implications for our understanding of the universe's origin, evolution, and ultimate fate. If our universe is a hologram, it suggests that the Big Bang, the event that marked the beginning of our universe, might have been a process of projecting a three-dimensional reality from a two-dimensional seed. This could also have implications for the nature of dark energy, the mysterious force that is accelerating the expansion of the universe. Holographic duality is a rapidly evolving field of research, with new discoveries and insights emerging constantly. As physicists delve deeper into the mysteries of black holes and the nature of information, the holographic principle is becoming an increasingly important tool for unlocking the secrets of the universe. Future research in holographic duality will likely focus on several key areas. One promising avenue is the development of more sophisticated computer simulations, like those pioneered by Rinaldi, to further explore the properties of quantum extremal surfaces and their connection to the holographic principle. Another area of interest is the search for experimental evidence of holographic duality, which could come from observations of black holes or other astrophysical phenomena. The holographic principle has the potential to revolutionize our understanding of the universe, providing a new framework for unifying quantum mechanics and general relativity, resolving the paradox of black hole information loss, and shedding light on the fundamental nature of space, time, and reality itself. As we continue to explore the implications of holographic duality, we may be on the verge of a new era in cosmology, one that reveals a universe far more complex and interconnected than we ever imagined.